TE analysis of the parallel plate waveguide. In this video, we're going to do four things. The first one is analyze the TE mode of the parallel plate waveguide. Then we'll go on and analyze that solution and talk about what that means. We'll finish by visualizing the modes and then conclude. TE analysis.
Here's our starting point. We are doing TE analysis. That's transverse electric, so the Z component of the electric field is equal to 0. That means we're solving our differential equation for H naught Z. We had a Laplacian here. I expanded that into Cartesian coordinates, so that's where the second order X and Y derivatives come from. And remind us this Kc is called the cutoff wave number, and it was K squared minus beta squared. This is very soon going to have meaning for us. And also to remind us, here's the equations for calculating the other field components once we have solved H naught Z. And we will make use of these. So let's look at our parallel plate waveguide. It is perfectly uniform in the X direction. We're also letting our mode propagate in the Z direction, so there's not even any phase being accumulated in the X direction. So literally nothing is happening in the X direction for our parallel plate. That means any derivative in the X direction has to be 0. Well, this is going to simplify our differential equation. We have an X derivative here. It's a second order derivative, but we cross it off. And so we're only left with one derivative in the Y direction. And in fact, there's only one independent variable left. So our partial derivative has become an ordinary derivative. And it's a much simpler differential equation. So we could hand off this differential equation to a mathematician, not even tell them what these different terms mean, and they can return the general solution to this equation. And there's really two ways you can write this. You can write this in terms of complex exponentials, or you can write it in terms of sines and cosines. So most people, when they're analyzing this waveguide, go with the sine and cosine solution. We have two constants to find, A and B, and those are found by applying boundary conditions. Now, our boundary condition, when we have metal plates, those are perfect electric conductors. The boundary condition is that the electric field, the tangential component anyway, is 0 at the plates. Well, here's a problem. We just found a magnetic field. We right now know H naught Z. And there really is no boundary condition for magnetic fields at a metal plate. We need to apply the boundary condition in terms of the electric field. So in fact, what we're going to have to do is go back and grab one of those equations for calculating the other field components from H naught Z, plug our general solution into that to get a general solution for the electric field, then apply the boundary condition. So for TE analysis, it's a bit more involved. So here's the expression we have for calculating E naught X from H naught Z. We will plug in the expression for our general solution, take the derivative, and here we have the general solution for the electric field. Notice we grabbed E naught X instead of E naught Y. E naught Y is not tangential to those plates. It's normal to them. So we can't apply the easy boundary condition of the tangential component being 0. So that's why we calculated E naught X. Okay, so now we have the general solution for E naught X. Now we can apply the boundary conditions. So our first boundary condition happens at Y equals 0, and our electric field has to go to 0 at this bottom plate. So we take our general solution and set Y equal to 0. So that means the arguments of both sine and cosine are 0. Well, sine of 0 is 0, so this drops off, and we're left with a cosine of 0. Cosine of 0 is just 1. So inside the square brackets, we're just left with A. Well, none of these constants in front of A can equal 0. So the only thing that can make this expression equal 0 is if A equals 0. So we found our first constant, A. It is 0. That means we'll find B by applying the boundary condition at the top plate. So at the top plate, y equals D. So we will plug in D for y in our general solution. Notice that first term we've already dropped because we know that A equals 0. So it's not there anymore. So if we choose B equal to 0, that means our entire general solution is all 0. Well, that's the trivial solution, and that's not what we're trying to find here. So something else must be making this expression equal 0. Well, j omega mu over kc, none of these can be 0, so that can't be doing it. So what's left then is this sine term. It has to be the sine term that is somehow forcing this to be 0. So we set the sine term equal to 0. Well, this sine function can only go to 0 when kc times d is an integer multiple of pi. Sine of an integer multiple of pi is 0. So that means our kc times d has to be an integer multiple of pi, where m is this integer, and it's 1, 2, 3, 4, all the way up to infinity. There's a few interesting points we need to make here. First, notice I'm not including m equals 0. It turns out this is not a valid solution because it turns out it forces all of the electric fields to 0, and that's not a meaningful answer. The other interesting thing is that m goes all the way up to infinity. And way back when we first started talking about waveguides, I mentioned there's an infinite number of modes. And that's where this happens. M can be any integer all the way up to infinity. And we can always keep going to higher and higher frequencies to find more modes. And the last point I'll make is that m is discrete. I can't choose a value of 1.7, for example. That's not a valid solution. It's an integer. So the solutions to our waveguide are discrete. The modes propagating in the waveguide are discrete. We will have a first order mode, a second order mode, a third order mode, and so on. And m will be our order of that mode. So we solve this expression for our cutoff wave number, and we get m pi over d, again where m is any integer other than 0. And we're going to use this expression on our next slide. So this was a really important slide because this was the origin of having discrete modes in a waveguide, having a first mode, second mode, third mode, and so on. Remember our definition of the cutoff wave number. It was k squared minus beta squared. If we solve this for our phase constant, because that's what we want to find here, we get square root of k squared minus kc squared. Well, in the previous slide, we derived an expression for kc. Let's go ahead and plug that in. Now we have an expression for our phase constant. But there's this m here. We have a bunch of different modes. And in fact, when we plug in different values of m, we get different values of beta. So each mode in the waveguide has its own unique phase constant. That means each mode propagates at a different speed. That's really a discussion for another class, but different modes propagating at different speeds can actually lead to problems and things like intersymbol interference, and it limits your bandwidth and other nasty things. We want to remember that this phase constant changes for each mode. So when we write this, we're going to write beta with a subscript m to remind us that's the phase constant for the nth mode. I went ahead and plotted some representative values of a phase constant beta for a parallel plate waveguide. And so for different wave numbers k, I'm plotting this phase constant. The red line is the m equals 1 mode. Remember, there's no m equals 0 mode. And I'm plotting the phase constant for different modes. And I can keep going, 8, 9, 10, etc. And so we notice that the phase constant changes with this wave number. More information, more meaning, and some interesting things will come out of this in later slides. So here's our final solution. We started with a differential equation. We got a general solution. Yes, we had to then calculate an electric field in order to apply the boundary conditions in order to get A and B, but we did eventually find an A and a B. Well, in fact, I should mention we didn't find a B. We did find that there's discrete choices for KC that satisfy our boundary condition. So we didn't find B, so we have to keep B. And B just becomes the amplitude of the nth mode. And so our final solution, we tack on the e to the minus j beta z. And here is our final solution for the magnetic field. Now, from that, we can substitute this expression back into our equations to calculate all of the other field components. So here is the total solution for the TE modes in a parallel plate waveguide.
Analysis of the TE solution.
Let's look at this thing again. Why not the zero order mode? Let's go to the previous slide, take all of those expressions for the field, and plug in 0 for M. Well, what we see is that all of the electric fields are 0. So the electric field is entirely 0. Yes, we have a magnetic field term, but for a propagating wave thing, that doesn't really make sense. So this clearly is not a physical mode, and so there is no TE0 mode in a parallel plate waveguide. Let's think more about this cutoff condition. This is where this Kc term is going to have meaning. So we derived an expression for our phase constant. It was the square root of k squared minus kc squared. So and really, in order for this to make sense, we need k squared to be larger than kc squared. That way we get a positive number under our square root, so we get a real value for beta. And that is why this is called the cutoff wave number, because if this becomes larger than k, this becomes a negative number, our beta becomes imaginary, and that really corresponds to a cutoff mode. It's not a mode supported by that waveguide, and all this is determined through that cutoff wave number. I'll also mention, just because the mode is cut off does not mean it does not propagate through a waveguide. In fact, it does. It's just that it decays very quickly. So with that said, let's derive an expression for the cutoff frequency. So our cutoff wave number is our cutoff angular frequency times square root of mu epsilon. And we have an expression for our Kc. It's m pi over d. Our angular frequency is 2 pi times the ordinary frequency. So the ordinary frequency, that's the one that's in hertz, kilohertz, megahertz. Now we can solve for this cutoff frequency. And we can put it in terms of m, d, mu, and epsilon, or we can also put it in terms of the cutoff wave number. This is probably the more useful equation, but you have both. And so we can use that to calculate the cutoff frequency for any of the TE modes just by plugging in different integers for m. And each mode will have a cutoff frequency. And at frequencies below the cutoff, that mode is not supported by the waveguide and will decay very quickly if we tried to excite the waveguide with that mode. Above that frequency, the mode exists. I also mentioned something else that's a little bit of an aside topic, but right at the cutoff, boy, things get really squirrely with that mode. And we tend not to want to operate a guided mode near its cutoff because really crazy things happen there. And we tend to operate at much higher frequencies. Wish I could go more into that because it's an interesting story, but I can't go into that here. Let's think about the characteristic impedance. So we define the characteristic impedance as the amplitude of the electric field over the amplitude of the magnetic field. And we have two different choices that we could do, the x and y components or y and x. So we derived expressions a few slides ago for E naught x and E naught y. So we simply just plug them in. We start canceling and simplifying, and we end up with an expression to calculate the characteristic impedance of the TE modes. Now that we've done the analysis, now we actually know this phase constant. So we're in a position to calculate the characteristic impedance. Another useful parameter is the effective refractive index of the mode. And the meaning of this is if we have a guided mode, it's interacting with the waveguide and traveling slower than it would if it were a plane wave traveling in whatever the material is inside the waveguide. And so we give it an effective refractive index to give it that factor by which it slows down relative to a wave in outer space. So our phase constant we can write as the free space wave number times this effective refractive index. Well, we have an expression for our beta. We derived that a couple slides ago. So that gives us an expression for the effective refractive index. We divide both sides by K naught. And when we do that, that's where we end up. So notice M is here. So that means each guided mode will have a different effective refractive index. That means each guided mode travels at a different speed, which can lead to problems or other interesting things. And so it also depends on these other parameters, the refractive index of the material between the plates, the separation between the plates. Another thing to think about, under the square root, we have 1 minus something. That's making this argument less than 1. So the effective refractive index is becoming less than the refractive index of the material between the plate. So think about this. What if the material between the plates is air? Are we creating something between those plates that actually travels faster than the speed of light? Let's do some calculations. Let's plot the effective refractive index for various modes, first, second, third order modes. Notice the effective refractive index is always less than 1. So these modes in this parallel plate waveguide seem to be traveling faster than the speed of light. How do we feel about that?
Visualization of the TE modes.
So here's a visualization of the first TE mode. Now this is not uniform because remember the amplitude profile had a sine cosine term in there. And we're seeing that. We're seeing a single hump of a sine with its peak right in the middle. And so one thing we'll notice when we're mentioning orders of the modes, whatever number here is how many humps we see between the plates. So we see a minimum to a maximum to a minimum. So one hump, that's clearly a first order mode. And so our eyes would see a bright spot in the middle of the plates. Let's look at the second order mode. So here we have 2 humps. It starts at 0, it goes to a bright spot, it goes to 0 again, back up to a bright spot, and back to 0. So our eyes would see 2 bright spots between these plates. That's the TE2 mode. And of course this would go. If we looked at the TE7 mode, we'd see 7 bright spots between those plates. Third order mode, we're seeing 3 bright spots. It's going to be hard from how many arrows I'm showing here to see anything higher than this, so we'll stop at this third order mode, but there's definitely 3 bright spots here. Conclusion. Here is a big, ugly summary of all the different equations for these various different parameters that we might want to do waveguide analysis, wave designs. Not a whole lot really to discuss here. It's just a summary of a bunch of equations, the field values, the different waveguide parameters if you want them. I've plotted the first 3 order modes. We have equations for the TE0 mode. We know that it's not a physical mode. I went ahead and plotted them and X'd them out to remind us those don't actually exist. Our TM0 mode, notice everything is straight and uniform. That is clearly the TEM. And here's plots of the other modes. And it's a little bit more obvious here how we are looking at 2 half bright spots. So there's our modes. So here's a summary of what we've done. We've calculated the fields for all of the TE modes. We've calculated phase constants, we calculated cutoff frequency, and we calculated characteristic impedance. And we haven't done the TM analysis yet, but I'm foreshadowing that we're actually going to get the same equation for cutoff frequencies. So that's nice because we can calculate cutoff frequencies for both at the same time. We also saw that the TE0 mode does not exist. That makes the TE1 the lowest order TE mode in the waveguide. And the lowest order mode is always the most important mode, because if we try to send power down the waveguide, most of the power ends up in the lower order mode. So that tends to be the one we work with the most. And a lot of times we only want a single mode to propagate in that guide. And why is that? That's because the modes travel at a different speed. So if we launch, let's say, the edge of a square wave and we excite both modes, if they travel at different speeds, that nice crisp square edge is going to blur and spread and cause bad problems. So very often we operate waveguides as single mode.
From the bottom of my heart, thank you so much for using EMPossible. I want to create more videos, and I want to continue to improve how electromagnetics and computation is taught online. To do that, it will really help me if you can like this video and subscribe to our channel. I also want you to know we have a lot more content that you may not be aware of. See everything we have to offer at EMPossible.net.